In this video, I will explain about the sampling distributions in statistics. The main objective of this topic, sampling distributions, is to distinguish between a parameter and statistic. And under the sampling distributions, we'll learn about the sampling distribution of the sample mean using the two important theorems, the Central Limit Theorem and the law of large numbers. We will also discuss about the sampling distribution of the sample standard deviation as well as the sampling distribution of the sample proportion. In our previous chapter, chapter 11, we talked about normal distribution, where the normal distribution is a bell-shaped symmetric curve. It is a continuous distribution with mean mu and standard deviation sigma, which is always denoted by the symbol n of mu sigma. And if we have family of density curves, bell-shaped curves like this, where the shape of the curve is the same but it is shifted, since the mean is the center of the distribution, the mean varies. The mean will be maybe 10 for this one, 15 and 20, but the standard deviation is the same. We can understand this by using some app. So in this app, you have a normal curve. When it is shifted to the right, the mean changes because the center of this curve shifts. The center of the curve, which happens to be the mean, it changes. The same way, when I move this curve to the left, then again the mean changes, but the standard deviation is kept constant. Since the shape of the curve is the same, the standard deviation is not affected, but the mean changes. Or, the standard deviation does not change, but the mean increases when you move the curve to the right and decreases when it is moved to the left. If we have a family of density curves like this, it looks like the center of these three curves is the same, but the deviations are different because you have a peak curve and you have a flat curve here and a mediocre here, the green one, where the mean is the same. 15 is the center for all the three curves, but the standard deviation may be 2, 4 and 6. 6 for the red one, 4 for the green, and 2 for the tall peak curve. So using this apex, so if we are shifting this curve vertically above, the center of the distribution is not affected. So the center is the same, mean is the same, but the standard deviation reduces. See, when you have a peak curve, the standard deviation reduces. Again, when you do it in the reverse process, that is when you decrease the height, then the standard deviation increases, but the mean is kept the same. Or the mean does not change, but the standard deviation decreases as the graph is stretched vertically and increases as it is compressed vertically. Now, the difference between a parameter and the statistics can be described using the population and the sample. The whole picture, the entire group is the population. And the results, whatever you get for a population, can be, say, mean, standard deviation, and proportion. And the symbol for the mean of the population is mu, standard deviation of the population is sigma, and the proportion of the population is p. So the results, whatever you get for the population, which is the entire group, the whole group, is the parameter of the population. So these mu, sigma, p These are all the parameters of the entire population. We can also find the mean standard deviation proposed for the small group, which is the sample, but we have a different notation for that. The mean is x bar, standard deviation is Sx. These are the things we learned in chapter 2, 3, and 4. And the proportion p hat, it is somewhat like your probability, what we learned in chapter 9. So the results, whatever you get for a sample, is nothing but a statistic. We use these statistical value to predict the value of the whole population. And that is the reason why this whole topic, the study, what we do here in Math 130 is Introduction to Statistics, because this course is all about learning how to use the data collected from the sample to predict the value of the whole population. That is, we are using statistical values to find the parameter of the whole population. That's the reason why this course is called the Introduction to Statistics. Let's take this question from our textbook on chapter 13, question number 17. The National Center for Health Statistics interviewed adults nationally, and 62% of the interviewers from that sample, a small sample, used some complementary alternative medicine. That is, in order to get values for the entire national group, adults in the entire nation, they are using a small sample, and 62% of that sample group are using this alternative medication. So this 62% is the result obtained for the sample. The results, whatever you get for a sample, is a statistics. So this bold face number, 62%, is the statistic for the data. Let's see this question 33 from our textbook. This will explain the concept of sampling distribution. It says we have a very small population of size 10 female students, and the weight of those 10 female students is given. The idea here is to pick small samples from this. So let us recollect the things what we learned in chapter 6. Whenever we pick simple random sample from a population, there are some steps to follow. Usually we check whether the population names of those people are given. In that case, we have to put that in proper order, and then, like in alphabetical order, then we have to assign or label the whole population. In order to label the whole population, you have to check whether the size of this whole population is between 0 to 10. If it is 0 to 10, you allot single digits to them. If you have the population with size more than 10, less than 100, less than or equal to 100, you are assigning 2 digits. More than 100, less than or equal to 1000, 3 digits, and so on. And here you have got only 10 female students, so you can assign them with single digits. It's already assigned, no name is given, so they have already assigned the number, and the weights of those students are given. You can find the mean of these weights by just adding all these weights and dividing by the total number 10. But the result what you get will not be x bar, because x bar is the mean of only a small sample. Whereas in our case, when you add them up and divide by 10, the value will be the mean of the whole population. The mean of the whole population is mu. So when you do this process, when you add them up and divide by 10, you will get the mean mu as 130.2. So that is the answer for A. Find the mean of 10 weights of this population, and that is the value for mu. Then use the first 4 digits in row 116 of table A. We know that this table A is from page 684 If you do not have the table with you, you can access your Sapling Plus course site. Under that, the file for table A, the random numbers, is given. This we used in chapter 6. So use line 116. Pick the first 4 digits. Again, when you're picking these digits, you have to be a little careful. If the numbers are repeated, then you skip that and then go to the next digit. So pick a simple random sample of size 4, write down the weights and find the mean x bar. So using line 116 of table A, when you are picking the simple random of size 4, you will get the mean x bar, which is an estimation of mu, to be 135.25. That is, we added all these values, we got the mean, the average of the whole entire population, which is mu, 130.2. Since it was a small population, we were able to get the value for mu. But in practical situation, if the population is of large size, then it is hard for us to find the value for mu. So we have to pick simple random samples from here. So the first simple random sample what we are picking is using line 116 and using the table A, which is in page 684 in your textbook. So in page 116, I think you get 14459 as the first numbers. I am picking, since I have already picked 4, I won't pick 4 again. So it is 1459. And the weights corresponding to these are, for 1, it is 99, for 4, it is 125, 5, it is 170, etc. You can find the mean of this. So this x bar will be 135.25. Now, if you repeat this process 9 more times by picking line 117, 118, 119, etc., the same process is repeated 9 more times. So for this whole distribution, we got the mean to be 130.2. By picking those simple random sample 10 times using lines 116, 117 through 125, we will get the samples and the corresponding sample weights like this, and the value for x bar, the mean for each sample, will be 135.25, 119.5, etc. So this 135.25 will be a representation for the whole population mean, or 119.5 will be a representation for 130.2. Each value here in this last column will be a representation for this. So this whole last column, what we get is, itself is a distribution. It is a distribution obtained from these small samples of size 4, and this distribution represents the sampling distribution of all its means. This distribution is the mean of all these samples. So the last column what we have is the sampling distribution of mean, or you call that as sampling distribution of x bar. We also know that these individual values are representations for 130.2. So if I want to get a single representation from this sampling distribution to represent mu, maybe I can add them up and divide by 10, which will be the mean of x bar. Now see, this mean of x bar, what I got is 129, which is very close to 130.2. In fact, this is the best representation for my mu. So in order to get a value for mu, it is better to find the mean of the sampling distribution. That will be the better value for mu. In this case, in this particular problem, we are not getting the same value 130.2, but if we are selecting a proper population, I said it is a good population only when the size is minimum 30. So if the size is sufficiently large, or if this distribution is a normal distribution, then the mean whatever you get for x bar will be exactly the same as mu. It will be exactly same as mu. Here, since it is a small population and we do not know whether it is a normal distribution or not, I think it is not a normal distribution. That's why the mean of x bar, what you get, is not exactly the same as that, but it is almost close to this. But if you repeat this process a number of times, instead of 10, maybe if I'm repeating this method, this procedure, maybe 10 more times, 20 times, or 30 times, or 40 times, or 50 times, then I may still get a better value, better mean of x bar, which will suit the value 130.2. For the same distribution, the result whatever was given for the sample, for each sample, instead of finding x bar, I can even find the standard deviation. So for each line what I have, line 117, 118, 119, etc., I can find the last column, not x bar, but I can find the standard deviation of this. So in which case the last column what I get will not be the sampling distribution of mean x bar like in my previous case, but here this will be the sampling distribution of standard deviation s with the suffix x. The same way, if I'm trying to find the proportion for these samples, then the last column what you get will be the sampling distribution of proportion p hat. So this is the method of calculating a sampling distribution. You can find the sampling distribution of mean x bar like the one what we did now in this particular problem, or instead of taking mean, you can find the standard deviation, you can find the proportion, etc. So this sampling distribution of mean x bar only is dealt here in this chapter 13. Maybe we will discuss that in chapter 14 too. And the sampling distribution of standard deviation proportion will be dealt in chapter 17 and 19. So in a sampling distribution, you have different random samples taken from the same population. Remember, we had the same population of size 10. We picked a number of 10 samples of size of the same size, 4, 4, 4. But there is a predictable pattern in the long run. A statistic computed from the random sample is a random variable. So all those x bar values what you got was not unique. You had variable values, so that itself is a distribution. So the sampling distribution of a statistic, it can be a sampling distribution of mean, sampling distribution of standard deviation, sampling distribution of proportion, because mean, standard deviation, proportion of those samples are all called statistic. You can, in the place of statistic, you can use mean, you can use standard deviation, you can use proportion, whatever you want, for whatever you get for a sample. The sampling distribution of statistic is the probability distribution of that statistics with a given size n. In our case, the size was 4, taken from the given population. It must be from the same population. Remember that. So let's take an example. Suppose if the original population mean is 100, standard deviation sigma is 15, and we have picked n equal to sample size to be 20. Then this x bar, the sampling distribution x bar, will follow a normal distribution with mean the same. The mean of the x bar will be the same as 100, and the standard deviation will be sigma by square root of n. So they have proved this result. That's what is the central limit theorem. I'll explain what the central limit theorem is. But if x is normal with mean mu standard deviation sigma, like in that example 13.3 what we did, your x bar will follow a normal distribution with the same mean mu standard deviation, not sigma, but this will be sigma by square root of n. In 13.3 we said here it was 130.2, this mu also was 129, almost close to that, but if it is normal the two values will be the same, and the standard deviation, if this is sigma, then for x bar it will not be sigma, but it will be sigma by square root of n. So if you have a population which is a normal with mean mu standard deviation sigma, the sampling distribution x bar will follow a normal distribution with mean mu standard deviation sigma by square root of n. Now in the beginning we learned that if the mean is the same, then you'll have two curves looking like this, drawn like this. See, the standard deviation for the flat curve is sigma, and the peak curve is the reduced one, sigma by square root of n. We know that sigma will always be greater than sigma by square root of n. Take sigma 7, 7 by square root 2. 7 by square root 2 will be less than 7. So for the flat curve, it is sigma. The flat curve is the whole population. So this peak curve, what you have is the sampling distribution curve. So when you talk about population and sampling distribution, the flat curve is the population, the normal curve describing the population, which we learned in chapter 11. This peak curve, what you have is the curve, normal curve for a sampling distribution, what we are learning here in chapter 13. So again, see, if you have just one observation, then you may have a flat curve. If you are repeating this process 25 times, 25 subjects, 25 times, n is 25, then you will have a peak curve. The distribution becomes a sampling distribution like this. So the central limit theorem says, when randomly sampling from any population with mean mu and standard deviation sigma, and if n is large enough in the sense minimum 30 and above, then the sampling distribution of x bar is approximately normal with the same mean mu, but the standard deviation will be sigma by square root of n. Maybe if we are writing this symbolically, I can say if x is normal with mean mu standard deviation sigma, the sampling distribution x bar will follow approximately normal with mean mu standard deviation sigma by square root of n. This n can be anything, even if it is small. If the original distribution is a normal distribution, then automatically this x bar will follow this, even if n is small. But if n is large, it can be from any distribution. It need not be from a bell-shaped curve. It can be from any other distribution. But the ultimate result, x bar, will follow a normal distribution with mean mu standard deviation sigma by square root of n. So whatever be the case, when you do problems in this particular chapter, you always remember that x bar is always normal with mean mu standard deviation sigma by square root of n. You will be given problems satisfying these conditions. So you just remember that x bar follows a normal distribution with mean mu standard deviation sigma by square root of n. We also have a law of large numbers. The law of large numbers states that the observed mean outcome for x bar, that is mean of x bar. See, remember in our example we got mean of x bar to be 129. That approaches the mean mu, that approaches that 130.2. 129 approaches 130.2 if the number of observation increases. So instead of 10 observations, 10 times we repeated the process instead of 10 times. If we observe it more than 10 times, say 20 times or 50 times or 30 times, then definitely instead of getting 129, you would have got a better result close to 130.2. That's what it says. Or if the number of observation increases, the mean x bar will be coming closer and closer to the mean of the population. The same way, if you're talking about the proportion of the sample distribution of proportion will be coming closer and closer to the proportion of the whole population. So the observed proportion p hat must approach the proportion p of this outcome of the population as the number of observation increases. So if you are trying, remember in chapter 11 when you are trying to find the area between the lower bound and upper bound of a normal distribution. So if a lower bound and upper bound is given, we use this key using our graphing calculator, normal CDF, the lower bound, upper bound, mu, sigma. And if you have area to the left, given in decimal, either in this extreme end or that way, then you know that you can use the key inverse norm, area to the left, mu, sigma. These are the things we did in chapter 11. But here, in this case, we have to find the area of a sampling distribution. So it is not a flat curve like this. You may have a peak curve where the curve is x bar, which is normal with mean mu, but the standard deviation is not sigma, but it is sigma by square root of n. What happens to the probability? The probability becomes normal CDF, lower bound, upper bound, mu. The standard deviation sigma is changed to sigma by square root of n. That is the difference between these two. So the red one, what we saw here, is the one what we did in chapter 11. The blue curve, the peak curve, what we have is for the sampling distribution, what we have in chapter 13. The same way, if the area is given in decimal, then in chapter 11 we said, in order to find the z value or the x value, the value on the line, if this value is unknown to us, in order to find the x value or z value, we use the key inverse norm, area to the left in decimal, mu, sigma. What happens to this peak curve, sampling distribution? You can use the same key inverse norm, but this will be area to the left, mu, not sigma, sigma divided by square root of n. If this one is z, you are giving a different name to this. It is not z, it is a z star. There should be a star here on top. Z star is inverse norm, area to the left, mu. There it was sigma. In chapter 13, it is sigma by square root of n. That is the difference between chapter 11 and chapter 13. To understand this, let us take some questions from our textbook, 1319. So from 1319 to 21, we have to use the same description here. The details are given that the cholesterol level is roughly normal with mean 130 and standard deviation 30. So your x is normal with mean mu, standard deviation sigma. Mu is 170 and the standard deviation is 30. If you are choosing a simple random sample of 4 14-year-old boys, 4 is your size, sample size, n is equal to 4. See the average cholesterol level. Earlier we talked about the cholesterol level. Cholesterol level is x. Now we are talking about not the cholesterol level, we are talking about the average cholesterol level. So the average cholesterol level is your X bar, not X. So X bar is normal with mean mu, standard deviation sigma by square root of n. So 170, 30 by n is 4, so square root 4. So the question here is, if you do this many times, what is the mean of average cholesterol level you get? The mean is 170. Mean is not altered. Mean is the same. So your answer must be A. And this 30 by square root 4 becomes a standard deviation. So if you are trying to find the standard deviation for the same thing, you know that the standard deviation is 30 divided by square root 4, which is C. In the next question, for the same data, you are asked to find the probability that the average cholesterol level, not the cholesterol level, but the average cholesterol level is between 200 or more. That is, you have to take the sampling distribution, not the ordinary distribution, because it talks about the average cholesterol level. So it is n 170 30 by square root 4, which is a peak curve. 200 and more than 200, that is 200 and above, so that is the shaded region, 200 and above. So how will you calculate this? You will be using your graphing calculator. You will use second variables. The lower bound is 200, upper bound is infinity, and the mean is 170. Standard deviation is 30 by square root of 4. Paste and enter. You get the normal CDF as 0.0227, which is 0.023. So your answer is A. It is normal CDF, the lower bound, upper bound, mean, standard deviation. Enter that. For this question, the number of lightning strikes on a square kilometer has mean 6 and standard deviation 2.4. There are 25 randomly chosen sample values. So n is 25, sigma is 2.4, mu is 6. So if you are what is the mean and standard deviation of the mean number of strikes? Here it is just lightning strike. Here mean number of strikes. So you are trying to find the mean of x bar and standard deviation of x bar. That is, you are trying to find the mean of x bar. The standard deviation is this. So the mean of x bar is 6 and the standard deviation will be 2 by square root 5, which is 0.48. In the next question 30, for the same data here, the number of lightning strikes is approximately normal with mean 6 and standard deviation 2.4. What is the probability that average number of lightning strikes, see the word average number of lightning strikes, 25 randomly chosen values is 4.8 or less. 4.8 is here, less than that, not for the flat curve, this is for the peak curve, because we are talking about number of observation is 25 and we are trying to find the value for the average number of lightning strike. So you have to use the value for this peak curve, which is normal with the same mean, but the standard deviation is not the same. The standard deviation will be this 2.4 divided by square root of 25. So the probability between this less than this will be lower bound is negative infinity, upper bound is sigma by square root of n will be, lower bound is this and the upper bound will be 4.8, will be normal CDF, negative E99, 4.86, 2.4 by square root 5, which will be 0.00. 0.262. You can also use that in your graphing calculator. Enter those values and see what it is. So for this question, heights of male students, suppose that the distribution of height of all male students on your campus is normal with mean 70, standard deviation 2.8. So if you're taking x to be the height of male students, it is normal with mean 70 and standard deviation 2.8. If you're choosing only one student at random, so it is just a flat curve, what is the probability that he is between 69 and 71 inches tall? So you have the flat curve between 69 to 71, which is the normal CDF you can use between 69 to 71 with a mean 70, standard deviation 2.8, which is 0.2790. The next question being is, what is the standard deviation of x bar for a sample of n male students? We do not know what n is. We know that the standard deviation of x bar is going to be sigma by square root of n. My sigma is 2.8. So it should be 2.8 divided by, I do not know what n is. I'll keep that as n itself. So it is 2.8 divided by square root of n. The second question is, how large a simple random sample must you take to reduce the standard deviation of the sample mean to be 0.5? So if this is equal to 0.5, you have to solve for n. If 2.8 by root n is 0.5, you can easily get the value for n. N will be 2.8 divided by sigma, the whole square, which will be 31.36. Though you have a value which is less than 0.5 here, you always go to the next integer. 32 is your final answer, because the rule says whenever you are trying to find the sample size and when you want to round it off, when the calculated sample size is not a whole number like this, it should be rounded up to the next higher whole number. So even if you have 31.01, I would have taken that as 32. So the answer to this B is 32. Next question C. What is the probability that the mean height of a sample is between 69 and 71? The mean height is your x bar. So it is for the peak curve. So for the peak curve, you would like to find between 69 to 71. So if you're trying to find 69 to 71, you need normal CDF 69 to 71, the mean and the standard deviation. You can enter that in your calculator and your answer will be 0.9566. So this video helped us to understand what is a sampling distribution, the difference between a statistic and a parameter, and what is a sampling distribution of mean, sampling distribution of standard deviation, sampling distribution of proportion. We also use the two important theorems, Central Limit Theorem, Law of Large Numbers. We did several problems from the textbook, and if you want to have a clear idea about this, you can try additional problems from your textbook. Thank you for listening and thank you for watching. Thank you.